Okay, back on business. Was a couple of questions during the break. It's like, what this has to do with HPC? And I got your point. It has a lot to do with HPC. I hope to be able at the end of the course it will be clear. But if you want an HPC library that does everything overhead free, you really need to know this kind of tricks. Or if you have enough work in your threads or tasks, and you don't need to have any efficient function call mechanism and stuff like this, that's fine. You don't need the C++11 or you don't need C++ at all. But if you really have some core thing that has to be efficient, you cannot rely on like virtual methods or object orientation. There was one of the guys, I don't remember who was it this morning, that says, I want to learn C++ to get more object oriented. And I realized that we don't do object orientation. This is not object orientation at all. Object orientation assumes that you have base classes and virtual methods, and you can cast objects of different types, a runtime polymorphism, and these kind of tricks. And we don't want to do that, especially in the innermost cores of our libraries, in our inner loops or something. We don't want virtual function calls at all. And this is why these techniques really kicks in when you don't want to have virtual method calls. And we will find out, we'll show you the example with the CRTP, the curiously recurring template pattern that I was mentioning before. It's like a way of getting some behavior from object-oriented world into an overhead-free abstractions. So no virtual methods, and everything will be efficient. Actually, there are some people that provocatively, they tend to say we should remove the keyword virtual from the C++ standard. As a kind of joke, because so much code rely on that keyword. But the idea is that really, before using a virtual method or a virtual function call, think twice or 3 times. I wanted also to show you something more about the template instantiation on this example I was showing before. I realized maybe it was not clear. So in this case, suppose you have a foo called with, this is the function we had earlier, right? That the function foo is just a template that prints x. And we call foo with 3400. We call foo int 65, foo char 65, etc. And what happens is the first 2 instantiations are actually the same function. So what I said before, right, you can instantiate the function every time you invoke it. It's not really actually true. Every time you invoke it with a different type. So there are these 3400 is an integer. It will instantiate foo of int. And this other one is foo of int 65 explicitly. They are exactly the same function. Let's go see the blue line and the yellow line. Okay, this is the foo int. Say this is the function foo int, which is like, okay, doing a lot of stuff because you have to print out things. You have a foo char. You have a foo double. And we have a foo with a string. And that's it. Then we have a main. And the main is simply calling void foo with 3400. Hope everyone can see. And it calls foo with 65. Okay? So same thing. There's only one function that accepts the integer. Only one instantiation of that function is called twice. The compiler is smart enough to not instantiate functions all over the place. Otherwise, you will soon end up with a huge binary code for no particular reason. And actually, if that function has static members, they are recognized. You know what static member, sorry, no, it's not a member. It has a static variable inside here. A static variable is something that lives not on the stack. It lives somewhere else in the global scope, basically. The first time you enter the function, the variable will be updated to a value, and then it will be just accessed every time you call the function. Which means if I have a static function, a static variable in here, the two versions, the two integers, will share that static variable. There will not be two static variables. Let me see. If I do like static t equal, wow, it's a problem. Static t, default initialized. Yeah, sorry. No x, y. Why is not? Why is giving me the error here? I go with the, no, I think the site is gone. Okay, yeah, okay, I don't know. So, that static t, there is one instance of that static for the integer function, right? For the function requiring the integer. Let's see. Maybe we can do it like this. Let's see if we can find it somewhere. Yeah, fooInt. This is a call to fooInt. Sometimes I put it on the back. Okay, this is a fooInt. There is some static. Okay, this is in here, right? My long static. Okay, there's a my long static in case my long static name instead of string. In the case of string. And there is only one, oh God. There's only, sorry, it's just way too painful. But basically, okay, let's go this way. This fooInt and fooInt will get a single instantiation of the function, and we'll have a single my long static name. So there's only one static function. So the first time you go and the static function is instantiated to 0. Okay, thanks. And the second time you go in, the static is already set it up. So when I call the first one, I set the static variable, I initialize it, and the second time here, I just use the same variable and update it. This creates a new static variable for the char, and this creates a new static variable for the double, and this is a new static variable for the string. But it's a single function. Another thing that might be interesting in this code is the fact that, let's go back to the original code so that we don't have surprises. What happened when we optimize the code? Well, GCC simply doesn't show any code around these guys because they will be inlined directly. So you go to main, finding main. This is a fooInt. Only fooInt is actually instantiated. Foochar, foodouble, foostring are not instantiated. You cannot find the function in the binary, in the assembly. But instead, you find write 65 into this register and call stdc out. Okay, so the compiler figured it out that it doesn't have to call the functions at all. It's still a mystery to me why the integers are actually called. But if you change the compiler into another compiler, like Clang 3.9, you will see the no code, no function is actually instantiated in the binary, so only main remains, and the other one is whatever exception tables and static variables. So it's compiler dependent what the optimizations will do. It usually works quite well. I'm really surprised that the integer is not inlined, but the usual functions are actually inlined, so there's no functions in there. Which is one point that I think I didn't mention this morning, is the fact that usually C++ code, when it's really highly optimized and everything inlined like this, makes your life very difficult, very hard when you try to use the usual HPC tool sets, like vampire trace to see function calls and what happens. Because the functions are not really there, so you cannot track functions there. If it does track functions, then it means that it's not optimized. So you have like you have a trace of the function calls which are not optimized, which defeats the purpose of using the tools to analyze performance. And this is a kind of downside, if you want, but it's really intrinsic in some sense. But we were left with sphinai, right? So the sphinai is like substitution failure is not an error. You want to see what happens in these cases. Now we have our struct x. It takes two arguments. The second one is an integer. I don't know why I said it like this, but the second one is by default an integer. And then we have xt with the extra type. Now we have different options, different classes here: struct A, B, C, and D. And they defined. This is the using keyword. Everyone knows what the using keyword is. Well, I guess everyone knows type def. Type def something to something else defines something else as a type, as an alias type for the other one. C++ 11 introduces using keyword, so it's using value type as an integer. And this is a kind of type member of this class A. Now B declare extra type, C declare extra type, and D declare extra type. So what happens? So we have two versions of this X. One is the primary template, and the other one is the specialization. So when I call X of A, what is the specialization being called? So which one says is the first? Which says is the second? Not many hands on. So the idea here is that XA, you go looking for the primary template, you go to the primary template here, A is the first template argument, the second one is integer, and now we go down and search for the specialization. Now we go to T and T extra type. Now A doesn't have an extra type, it has a value type. There's a difference, so it doesn't match, and you get and this is sphinai. So sphinai kicks in, so this guy will be thrown away as a non-valid candidate, and you stick with the primary template. The second one is B, right? XB. What happens in the case of B? Who says the primary template? Who says the specialization? Okay, let's analyze it. Goes to the primary template of B, and the second one is integer. Now he searches for the specialization that holds. Now he goes here. This is B, and this is B extra type. B extra type is integer, exactly the same as this guy. So he's looking for B int. Okay, this is looking for a template with B and int. And this is B, and B column extra type is int. So this is the specialization which is picked up. Is clear to everybody why? Now let's go with C. Primary or specialization? Who's for primary? Take your time to look at the code. Who says primary? Who says specialization? So what happens here? XC goes to the primary template, and there's no second argument, so it searches for C and int. Now C, extra type, is float. So it's not int. It's looking for C and int, which means this goes to the primary template. Confusing there? It's not that confusing. You need to get used to it. Remember, when you look for the template, you look first for the primary template. Now I'm specifying C with a single template argument. Now I go here, so the second template argument must be int. So I'm looking for, in my specialization lists, if I find something which has a C and int and matches and goes and actually match very well what I'm specifying. But C extra type is float, so it's not int, it doesn't match, you go to the primary template. This should make things clearer, because now if I want B and char, what happens? Well, I shouldn't have clicked. But what happens in this case? So B and char. Let's see, try to apply the reasoning. Who's for the primary? Who's for the specialization? You got a few confused people here. So B goes to the primary template and say I want to instantiate B and char. Now B goes search for the specialization then. Okay, I put B here and I put int here. Well, sorry, B extra type, which is integer and is not char. So I go with the primary template. Let's see if I'm right. Primary template. And finally, D, let's go to the process. I want D and char, go to the primary. T becomes D, and U become char. Now I go down here, D and D extra type. D extra type is char. So char matches, which means I go with the specialization. Oops. This is a very convoluted example just to show you the things that happens, right? There's no real code of whatsoever kind, but it shows you the mechanism. So always go to the primary template, figure out what you're looking for, search through the specializations. So what is Sphina good for? Basically, what happened is the following. Around 2000 something, 2001, 2003, people start realizing that these things are not only rules for the language. You can actually exploit these behaviors to do things for the good or for the bad. But so there is one thing in the standard library which is called enable if. It's kind of a meta function that exploits this Sphina mechanism. Let's see what we have here. Do I have the example? And the void t then. Okay. We have a class, a template. This is the primary template, which doesn't have an implementation. It's just a declaration, right? So this is technically incomplete. So if it happens to instantiate this, you get a compiler error. Requires two arguments. The first one is t, and the second one is equal to void. You can use void as a template type, as a template argument, by the way. And this is just a kind of rule to say, okay, this guy is not supposed to do anything, to be empty. And then we have specializations. And the specializations work like this. You have a specialization for which std enable if is the same t int colon value void colon type. Or std enable if not, std is same t colon int colon value void and type. Now, what is it doing? Who wants to tell what's happening here? Okay. So I want to now instantiate an object of my class A with a template argument. And let's say that my template argument is an integer. I want to instantiate A of int. All right? Let me okay, it's a little bit down there. So inside my main function, I want to do something like this. A of int equal x. Go to the primary template. You say, okay, type name t. T is an integer, and the second argument is void, because I didn't specify the second argument here. And then I go search for my specializations. My specialization says, okay, listen, the second argument here can be std enable if, and this guy. So this guy, std, is same, is a type traits, that's the same that we used earlier in the example. It gives me true if the two types are the same type, otherwise it gives me false. So if t is int, this is true. And if this is true, enable if return with quotes, gives me void. Enable if colon type is void. In this case, then these matches and I go into this specialization. Here, I go down here. Now I try also the other specialization. The compiler tries all the specializations. So it goes down a int, and this is not same. So whatever this t is integer, this is false, and this is sphenae. This is a substitution error. So this version will be thrown away. This one will be thrown away, and this one is the only surviving candidate, and you get integer. If I want to do instantiating a float, it will be the other way around. So this will be t will be float, this will be false, this guy will be discarded, will be substitution error, will be thrown away, and this guy is true. T is not an integer, and so it will go not an int. Do you want to see in action? Or are you convinced that is working? This is quite tricky code. There's a lot of stuff going on. There is std same, colon value, and colon type. This is getting into metaprogramming, okay? This is going inside metaprogramming. But this is actually a good trick to use. Now, in C++ 17, there is something called void underscore t, which uses a nice feature that is decal type, the one that we saw before. But I'm not ready to show you this at the moment. Yeah, I will show you later. Let's see how we can generalize our code then. So we got the sphenae, the enable if. We will see enable if other times. We will see void t. We'll get used to this concept. Now, let's say that I have a class, which is my container. It has a value type of integer, and the container type is vector of that some value, and I instantiate the container C as a data member, and my container as a constructor would take size and CS. Is this code clear to everybody? I assume it is. If it's not, please raise your hand. I can explain what that is. So when I instantiate my container with 42, I call this constructor, and I instantiate my container, my vector, of size 42. The problem is that my container is not flexible. It can deal just with vectors. It can deal just with these integer value types. So this is a container of a vector of integers, basically. Instead, I can use a template, and I can generalize my code. This now enters into the realm of making the code flexible for other purposes. Just if you're developing your application that does one thing, and it's totally fine to use the other container. You need a container of integers, just use a vector of integers, and no one will complain about it. But if you have to give your code to someone else, and you want it to be flexible, maybe you want to do something like this, in which you create a template class, in which the value type is actually passed by the user. So I want my container of integers to be size 42. So I will instantiate a vector of value t at this point, and value t is whatever template argument, and I get the same results as before. I have to use, of course, the angle brackets to specify my type. But a vector has actually two template arguments. One is the value type, and the other one is the allocator. By default, the allocator of the array is the standard allocator that allocates something on the heap and does a new statement somewhere. And now I want to say, well, listen, I want to pass the value type plus the allocator, and by default, this will be the standard allocator. Assuming here I'm using a namespace std, so it's std allocator with this vt type. You see the thing I showed you before, vt is defined here, and I'm using in this other line, in this other statement here. And now my container is a vector of value t and allocator, and I can allocate my container of integer with 42 size of integers. I can allocate with std allocator of integer. In this case, I explicitly say what allocator I want to use. Or I can even pass an allocator of double, but this will give me a compiler error because the vector will check that the allocator is allocating the right type. So this last line is not valid at all. But it's allowed. I can write this, and I get a compiler error. So we want to customize the allocator. So this guy cannot be called, right? So instead, we can do a trick to reduce the redundancies. And we can use what is called the template argument. So far, we've seen the templates are assuming to get a type as an argument. You get a type, and you do whatever you want with that type. But you cannot pass a template that is an incomplete type. Well, in this case, you can pass actually an incomplete type. So I can say template type name class allocator equal allocator. What does it mean? Allocator, the standard allocator is a template which takes the type that you want to allocate, the value that you want to allocate. The class here is mandatory, is the keyword you have to use. So it's template type name class allocator. Here I'm saying allocator is a template which takes one argument, one template argument. And now, well, my container type will be vector of value type of an allocator with value type. So I cannot make mistakes anymore. I cannot pass a value type of integer and allocator of a double, because the allocator will be automatically selected for the integer. And so I can write my container int std allocator size 42. Flexibility. Some cost, some time, but it is template arguments may help. Well, one might ask, why don't do simply this? My container of vector int allocator int, possible. You have just a single container thing. A value type is container column value type. And the container T is just a container. This is exactly the same code as before when I say vector of allocator integer. The only thing is that whatever container I'm passing in must have the value type defined inside the class. Now the vector, all the standard containers have it, but if you want to use your container, like your customized container, you must implement these things here, which is not necessary before. So instead, we can customize everything. We pass a value type, we pass the container we want to use, and the allocator we want to use. And these will have a template argument, which takes my container takes two arguments, the value type and the allocator. The allocator is a template that takes one argument, and then the value type is VT. The container is value T with allocator value T, and it's two different arguments. You see, this is the first argument of the container, this is the second argument of the container, and we get this behavior in which I specify simply the things I want to use. I can use int list allocator, int map allocator, or different allocators, and I can do all this trick. It's up to you. It's up to, well, there's an extra thing that is value type is allocator argument. It's up to you what you want to provide, what API you want to give to your user, and that template arguments might have some issues sometimes. They're not so general at the end, but basically this allows you to specialize everything. You have a single short template that allows you to specify all the possible combinations. And performance-wise, this is just, it will work like instantiating, replacing the strings in there, and instantiating the object, and everything will be as good as if you wrote your class as if you wrote the thing for the vector, the allocator, and the integer. So if I write the first version that I wrote, and I write this one, they have exactly the same performance. Right? There's no slowdowns of any kind. Is it clear why you don't have any slowdowns? The idea is that you really write the code, the compiler generate the code using your strings that is going to substitute in there, creating your instantiation is the same, will be the same code as you were writing in the first slide of this series. And so the performance is exactly the same as that one. But you can create a layer on top, right? Now you don't have a vector, you have my container, and then you can do even more things that the vector doesn't allow you. And you can give to your user, wherever the user is, maybe yourself, a better looking API for write your programs. The problem with these things is that every example that I came up with looks very artificial and very kind of so what. But in every example that makes sense is going to be extremely complicated to explain it, to put in slides, right? Yeah.
Requirement argument of the template, the container is the allocator.
Yep.
Is there any way that we can combine enable if and with the case that we only have a container that does not have the second template argument, the allocator itself?
I'm pretty sure you can. Now I have to think on top of my head how to do it. So in case you don't have that, well, first of all, to do so, you need to, this cannot be the primary template anymore. The primary template must be different, and then the specialization should have these extra template arguments. I should try it out. It should work, but I should write the code, basically. What do you think?
To have like several variable number of templates in the CT.
No.
Basically, basically, in the case that I have a vector that receives as a second argument, the allocator can use that. But if I use my own container, which does not receive a second parameter allocator, can I have it without it?
You can
because I always have allocator there. All the time.
You can do it if you use a variadic template.
Yeah, there are several. So the question is, if my container, if it's not a vector but my own class that doesn't have an allocator, how do I do it? I guess this primary template does not work. You need to change the primary template, and then you can play the tricks. Maybe variadic templates, as we seen next, but also I guess just a specialization for the case in which you don't have the thing. Oh, it was in C++ 98. It was already there. Yeah. We've seen these using statements around the code that I showed before. It's like a type defs on steroids. Type def is like, you do. I don't have an example of type def. Everybody knows what a type def is, I guess. The type def, int x will define x as an integer. It will be the same type, just a different string to identify the same thing, but it's exactly the same type. And using is just exactly the same. If I using integer type equal int, that's just defining integer type as a alias for int. Why do you want to do that? Well, there are many cases in which you really want inside your classes to use different names, and it's very common. It's just as using type defs. The advantage of the using statement is that you can put template on it. You can have an alias template, which is type def template type name t using type vector t, right? And then I can simply say type angle bracket double, and that will be a type def for the vector of doubles. Do I have it here, or it's not? Yeah, this is just, okay, yeah, okay. Can give you an example, I guess, using type. So then I can do type x So now I can do type double x 100, and I get a vector of doubles of size 100. Okay, because I'm doing an alias template, the type is just an alias for that guy. So the using statement can handle template arguments, default template arguments as anything else. So you can have something like, instead of the class that we were talking before, the my container, you can just do it with the type def using a single using statement without any further code by using my template to a lock cube, and you see that t will be the container, you the value type, and this is the allocator, and this is by default the standard allocator. Okay, and there you can do, again, something like this. Maybe I can use my container in the vector int my container. Right, so now I can do my container, vector, integer, and this will allocate with the standard allocator a vector of integer of size 100. Right, and this is the same code that we had earlier, only that these are swapped because for some reason I did that like that. But the idea is that now there's no implementation here, it's just a type def with templates. You have to remember, though, that the using is really a template. So is really a type def. It's not a type. It's not a class. It's not something that you can use independently of the original type. So let's say we have like my vac, which is a standard vector of type T, and my locator decided to put in there. And this is my vector. And now I have a size of function which takes my vec of t and return the size. Now v is a standard vector, right? So this v dot size is defined as anything else in vector because my vec is just an alias for a vector. So this will be vector of t allocator t dot size and gives me the size of the vector. Now I want another function size off, in which I want my vector of t, my allocator, to do the same, but just for the std vector instead of my vec. And what should happen here? Should this work? Should this code compile? Who says it's going to compile? Who says it doesn't compile? Okay. The code doesn't compile, and the reason is my vec is the same as this guy. It's just an alias. It happens to have a different name, but it's an alias for the same thing, standard vector t, my allocator t, which is this guy. And this guy is exactly the same. The compiler says, well, there are two implementations of the same function. I cannot choose one or the other. So you get, this is ambiguous with the other one. You get an error that says this function is ambiguous. I don't know what to do with it. Let's see if we can work through this example. Now we have a main that calls the function do nothing, passing my vec of integer of size 23. And we have a do nothing with v int, my allocator. We takes a template argument class v, int my allocator int, and the other one calls v int with a single template argument. This is tricky. Let's see if you can work this through. Do nothing takes my vector of integer. And so what is my vector of integer? Well, it's std vector t, my allocator t. So you go here and say, well, look, I have my vec is actually a std vector t. So this is actually a template. An object with is a template with two arguments, and one is my allocator, and the other one is integer. Sounds like a very good match. This guy expects a class with a single template argument, and it's simply never picked up. Is never picked up because my vec does not have a single template argument. My vector is an alias for this guy which has 2 template arguments. Okay? So this guy is never picked up. The second version of the do nothing is never picked up in this code, is discarded by the compiler, never instantiate anything like this, and only the first one will be instantiated. Is it clear? Is it clear to everybody why? So my vec, which looks like a type with a single template argument, is actually an alias for a vector t and my locator t. So you should substitute here vector t by locator t 23. And this matches a do nothing which takes a template with 2 arguments and not with 1 argument. So alias templates are very, very powerful. It allows you to do a lot of things, but you have to be careful that they are not objects. So if you really need a type, like a type or an object which is must have a different type of some other object, you need to declare a class and not do it with alias templates. Any questions so far? Yep.
So is anything about templates reflected at runtime? Nothing, right? It's all disappears at compile.
What remains are the instantiations, the successful instantiations. So those functions that we were looking earlier, right? The foo, int. These guys are actually instantiated, and they will be called. Also, objects, classes will be instantiated. They will have code representing them in the actual binary.
So to make efficient code, do you have to formulate your templates? Is there a good way to formulate your templates in order to get efficient code ultimately? Or is it
Not really.
to the efficiency?
Not really. Writing a class, let's say, or a function without templates gives you the same performance as a template one. The mental model is that you substitute the text for your types into your class templates, into your function templates, and you instantiate that thing. So here, if you go, oh my God, what did I do? All right. Total blackout. Okay, let's remove the O3 and go to the O0. You see these different colors there? There are different implementations of the functions. They are there, and they're called like this. So the name of the function is foo angle bracket int. That is the function you create. There's no function foo. Okay? Foo is not a function, it's a template. What exists is a foo angle bracket int. That is the function that is instantiated. And it's actually not instantiated like this. It is instantiated as a mangled name. It will be instantiated as a weird name that you have to filter out to understand what it is. And the reason why it's mangling is because it must be unambiguous at link time. You need to be able to understand exactly what version you are referring to. This is a technical aspect, but it's quite important in C++. But basically, if you demangle the names, then you get foo, int, and int, whatever. Other questions before we go into variadic? Because variadic templates are interesting. So C++ 11 introduced variadic templates. So far we have seen templates that it takes 1 argument, 2 arguments, 3 arguments. What if my class takes an arbitrary number of arguments, or template arguments. Well, before C++11, you had to do it by hand, writing all the possible versions for 1 argument, 2 argument, 3 argument, 4 argument, 5, etc. And there were tricks using Boost preprocessor library that were extremely ugly, very, very difficult. But with variadic templates, you really get to the point. Why you want to do that? Suppose I want to provide to my user an API to process 1, 2, or more data items. And I don't want to write like a C or Fortran, which I have function name underscore 5, so then I pass 5 arguments. Or foo underscore 3, so I pass 3 arguments. I want to just give the 3 arguments or the 5 arguments. And that will work even in C++03. That will be definitely working, but the implementation is quite complicated. And it requires you to write by hand everything. C++11 provides you the variadic templates and say, okay, I will have a certain number of template arguments. I don't know how many. We'll figure it out at instantiation time. This leads the introduction of the argument packs. Argument packs is just something which is expressed using 3 dots. Some of you might know that C and C++ already have the 3 dot syntax for instance, printf, in which you can handle an arbitrary number of arguments. You pass a function and you pass many, many arguments on that. And that uses a runtime mechanism that basically goes and marches through the arguments and figure out the type they are according to the format string or something. Now you can use the 3 dots also for templates. And the syntax that I have to use is like if I want a template version, variadic template version of my foo function, I have a type name, ... teas. I use the S here to specify that there are more than 1. And then foo takes ... args, which are the runtime arguments. Now, foo at this point can use these arguments as it wants. For instance, it can do pack expansion. Let's see. So TS is a parameter pack. It's a bunch of types. And you can assume it's like integer, float, double, char, struct X, whatever. This is called pack expansion. So you put the 3 dots after the args, and you call the function with these expanded arguments. It's like, okay, this is integer, float, and char. This will call the function with 3 arguments, integer, double, and char. There is pattern expansion. This case here is a special case of a pattern expansion. Pattern expansion takes the ... and takes the pattern and repeat the thing for all the arguments, putting a comma at the end. So it will be, this guy will be pattern arg0, comma, pattern arg1, comma, pattern arg2 until the end, without the comma at the end. It's a pack expansion. And it can work also, for instance, getting here the address of all the arguments. So this guy will call the function with address of argument 0, address of argument 1, etc. Okay? So far, it doesn't look that complicated. This is for the function template. Let's see for the class. You have a struct A and type T, and you can go and get any number of arguments. Now, it works as before. When you instantiate template, it's only when you instantiate it that it is created somewhere in the code, right? I want to instantiate a class with 3 template arguments. Fine, I can do it. And when I pass 3 arguments, it will create the template with 3 arguments in the code. So it never creates this dot, dot, dot. The code never sees that. It sees the actual implementation, the actual instantiations that you requested. There is a special cases of this pattern expansion, like size of dot, 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 t gives the number of arguments. So for instance, here you can have a list of arguments, template arguments, and a column count will be the number of arguments that you specified. So this is a kind of special size of. The standard provide a standard tuple, which is what already mentioned earlier. Is just a sequence of types, and that a sequence of values of different types. And you can say that the type of STD tuple with these types, so I call it tuple. And I can do expansion with pattern. I want a vector of tuple of vectors of t's, and expanded. This is a pattern expansion in which you have a STD vector of integers followed by a STD vector of doubles, STD vector of float. And you can also do multiple things, which is the zipping. This might be very useful sometimes. STD tuple. I miss a piece here, yeah. But basically the idea is that you have a STD pair of t, and STD vector of t will create a pattern in which you have a pair of integer and a vector of integer, then a pair of double and then a vector of double, then float and a vector of float. This is called zipping. And then you can have a constructor that takes these t's and accepts those arguments. Now, it's only when you instantiate it that you create it. So if I create my class B with integer and char, here this constructor will take an integer and a char and requires the data, which is the tuple, to be an integer and a char. Okay, so this code is never instantiated as is. The dots will never be part of the code. It will be instantiated with the number of arguments that you requested. It means that a B with 2 arguments is a different type from a B with 3 arguments, no matter what the types are. Is it kind of clear how the syntax work? This is just a matter of syntax, basically. And the type substitution, I mean, the string substitution should be fairly clear. Let's see it in action. I want to have a function prettyPrint that prints on STDC, that prints on a stream, and the stream STDC out. And I want to print 3.2, hello, 42, and word. How does it work now? How could I implement this using variadic templates? Now, I have a prettyPrint which takes 2 template arguments. The first argument and the rest. Now, the first argument of the function is the stream, in which I want to put stuff on, which is cout in this case. Then I have the first argument and then the rest. Then I print the first with the curly braces, and I call prettyPrint with the rest of the values, and I expand the values. And then I have a base of my recursion, which is just take the O stream for finishing up. Yep?
I wanted to avoid the recursion. I could also use a for loop with the size of.
No. A for loop, sorry, the question is, can I use a for loop instead of doing a recursion? No.
Because I cannot access value.
Yeah, exactly. And because the value has a different type. So in a for loop, this is an interesting question, right? You have a for loop, and you are iterating through your values. Now you have a x something. You assign x to the value to the first value, and then the second, and the third value. Now x has a single type that cannot be changed at runtime, right? It has to be once x is defined as a one type only, which means that if I'm marching on, the first x will be integer, the second one will be double, but wait, too late. X is already an integer, so I do a cast or something, or I get a compiler error. So recursion is basically the only way in which you work with variadic templates effectively. Is that kind of clear? Yeah.
So runtime, the instantiated pretty print, will there be recursion or there's no recursion?
Okay, this is implementation dependent. Usually it does not.
So
If you optimize, yeah, if you optimize, it should go away. We can, we can try. Okay, variadic templates. Why is not already? Ah, Clang. Okay, yeah, you're right. I usually use the other one. Okay, warning. So let's compile the slide, the code in the slide. And here, without optimization, you should see something disturbing maybe, but this is the basic of the recursion. Pretty print std basic o stream with no arguments. Then you should see pretty print with double constant int and char const start. Then there's got to be another one later on. Pretty print with const, char const, int and char, int char const char, const char const pointer, then one with char const pointer, and that's it. So you have all the implementations, right? So first of all, the one with a single argument, which is a const char, the actual type that I requested. Then the one with an integer and a char, and the const char, char const pointer, int const char pointer, and the final one with the double and the other arguments. And on the top here, don't ask me why it is on the top, is the base of the recursion. We realized at some point that the compilers put the non-template functions before and the template functions after main. For some reason. We still haven't figured out why. It shouldn't be a big deal. But, so this is the mechanism. In theory, and only in theory, I guess, I don't know what Clang is doing, but if I put O3, there shouldn't be function calls. Yeah, you see there are no function calls. Everything is in line. And you just pass the thing on. So when you optimize, the compiler flush everything out, which might be a problem when you try to step in the functions and you don't know where the hell you are. But did anyone here programmed in Lisp or Haskell? Anyone else? Yeah? Lisp. Prolog? Yeah. Even. Okay, that's surprising. Yeah. Okay, so those are functional programming languages in which you simply generate new stuff all the time. You process lists of elements, you create new elements, and you don't have the concept of reference. You just return things ex novo. Variadic templates and general template metaprogramming is that kind of programming, okay? When you program those things, you program exactly as you program in Lisp, only that it's all compile time, so the error messages are a little bit tricky, but actually I think it's even better than Lisp, because Lisp you never know what the hell happens at runtime. Here you get an error message at least when you compile. But you see, this is recursion, right? You have a list of things, which is T and T's. You take the head of the list out and you work on the rest of the list, and you go on until you empty the list. It's actually quite easy, and actually, if you have seen, the optimized code doesn't have recursion. So it's not, it is performance, it is efficient. Do you like it? We mentioned tuples. I think there's just one slide about tuples. Paolo will talk more about tuples. And I don't know why it's here actually. I have something else in mind. But a tuple is just a sequence of elements with different types. And you have a tuple of integer, a string, and a float, and you put in there. And you have the get method to get the value, but you have to specify that also the type. And you can get the tuple and tie up those values to your variables inside the program. And what I wanted to say here is that the C++ 17 will have a nicer thing to return multiple things and tie it into your local variables. But more on the tuples will come with Paolo's presentation. Okay. Now, I realize that at this point you might want to do some exercises, but the template exercises that I concede was a little bit too complicated. So instead, since I don't think it's worth it starting with the move semantics, since it's almost 5, and maybe we can go through an example and see how these things can actually be used to create some API that might be nicer for the user or something. Does it sounds like a plan?
If anyone has something which is unclear.
Yeah, if any questions, please. Anything, really. Not personal, but anything about C++.
I have a question for the template specialization part, which you covered pretty much for classes.
Yeah.
I thought to remember that there was something weird about how that translates to functions, like having different specialization, mixing templates with overloading and something like that.
Well, you don't usually talk about specializations for function and function templates. You talk about overload and overload resolution, which means that whenever you call a function, the compiler tries out all the possibilities, including the templates, which are not evaluated, will be just checked for the signature, like in a decal type, right? In a decal type, for instance, you get it is not evaluated the structure. You just do it. You just check that the signature is right. So the compiler basically tries out all the possible things and then instantiate the successful one. A function, usually, if you specify a function, it is assumed that this function will exist in the binary. So if I have a function, like an int foo takes an integer and something is doing, even if I don't use the function, that function will be reflected in the binary somewhere. That is the assumption. If you really want it to be included, it has to put the keyword extern to be really sure that the function is there. A template is only instantiated when it is used. It means that if you have several options and the template is not picked up, the template does not exist in the final code. I don't know if that answered the question, but I don't know exactly what if you have for more specific comments.
Maybe I can add something to the thing. So the specialization for functions is somehow also. So if you need to specialize for a function, usually you use the template default argument from C++11, which does not exactly the same as the specializing, but
Yeah, it's kind of
usually you can solve similar problems. Otherwise, for having a specialized function, what we usually do is to define a functor with template parameters and then use the specialization for the functor, which is a struct or a class, which overloads the parenthesis operator. So you can use it as a function, as a callable, but it's not exactly a function.
Yeah, a functor is a class that, as Paolo was saying, defines the parenthesis operator or the function call operator. So if you that allows you to do real specializations like template specialization classes. Otherwise, you really have to work out with overload resolution.
Yeah.
Well, we have seen variadic templates, so I can show the void T example, which is a new addition to the C++ 17. One of the cutest one is a really cute addition. Wait a second, we can do like this. Okay. Oh, no good. So, what is this code doing? This is a new addition that will be on C++ 17. The std namespace would include this guy, exactly this code. An alias template with variadic template, which defines void. I don't expect people to get it like this. It's really quite a trick. Suppose that we have a function. Let me show you the code. Everybody see? Everybody can look at the code? You have this little token here. This is a void T. And let's go to main. Always go to main. And we want to sum. We want this API. We want to be able to do a sum or integer and do an adding 3 and 4. So we have the sum function. You have the struct sum, which is a template. And the template, it is the primary template. They always have to exist, right? The primary template. And then takes a T and then this void default argument to void. Defaulted to void. Void is idiomatic, meaning that there's no special meaning in the void. It can be int, it can be float, but it has consequences to something else. But basically, just a choice to put void. Okay? And this has a member function, which is a static member function, which add t and says, well, really, I cannot find any operator here. Now we go here and say we have a specialization for one argument. Sum t, void t can add t, and then return a plus b. What is void t doing here? Void t is an alias template which takes an arbitrary number of template arguments. And the trick is that can add is another alias template. It's over here. All right. It's decal type, decal val c plus decal val c, where c is a template argument. Okay. Now, let's follow one implementation with integer. Okay. Now we have an integer here. We want to sum int add 3 and 4. Sum int will instantiate, goes to the primary template and say, well, this is integer. It goes to the specialization. The specialization says, okay, void t, is looking for now int and void. Okay? And now it goes here and says, void t can add t. Now, can add t is going to say, t is an integer now, is int. They say, well, decal val of int plus decal val of int, it actually exists, and return an integer. Oh, okay, then can add actually goes here, and it actually exists, so void t now is void, which is exactly the type I was looking for. So this will do 3 plus 4. Let's just get to another. Yep.
Just a little bit.
Where is it? This way or the other way?
I think it's in that.
Have you heard anything I said? Okay. Let's go see another version. You have a class B, which is contains a string data member, and is constructed with that string very easily, not complicated. And we have an operator plus defined, which takes two arguments, a b, and returns a b, which basically concatenates the two strings with some spacing in between. And then we do sum b, add b, hello, and word. Now this guy goes through the same process. He goes through the primary template and say, well, listen, I need type b here and void. This is my primary template. Now I go down, he looks for specialization and says, listen, this can add with b. And it goes b can add, and it looks for decal type of b plus b. And there is an operator plus defined for b. So this will return, decal type of this guy will be, I think, a b or string, I don't know exactly. It will do something that makes sense. And so this will go here and do a plus b on my b type. When I go here to sum a is this struct here, is an empty struct. An empty struct exists. You can be instantiated, can be copied, can be moved, can be everything. It just doesn't do anything. It has an operator streaming to print something, but that doesn't mean anything. It doesn't have a plus operator defined on. Which means that when I go here to find for the specialization, can add, this guy tries to do a plus a, and it doesn't find the thing. And it says, well, this is a substitution error. This cannot possibly be done. This is sphenae out. And so only the primary template will remain. So if we go here and say make void t, and we run it, so for int, we have output is 7. For b, the output is a hello word. And for a, no operator found to sum add a, and for the class A. This string is printed by my show trick, right? That shows the code that I'm actually trying to do. It's very simple trick. But so you can see that this thing works. Any question? Do you find it interesting? So it will be in the standard in C++ 17, but it's a couple of lines of code. You can use it anytime you want. Now, what I wanted to show you also, in the spirit of this course, it's a library version of it. What do I mean, library version of it? I want to provide a library to my user to be able to call that sum and do whatever he wants to do. And I want to actually to do, for instance, I can throw exceptions if something goes wrong. Instead of printing something, I throw an exception. So my library here, it is within a namespace, which is my name, my library, my word is in there. We have a namespace detail, which is something I don't want the user to be exposed to. The user will say, the only thing the user will see in this library is this function here. Oops. Is this do sum. Okay? This is the only exposed API at the my library level. And the detail namespace contains this trick with a can add, which tries to add the two values. If it can, it gives me something decent. And then implement exactly the same thing, only that instead of, this is nice to this string. Anyway, yeah, this is wrong. But it will return a string in this case, but it's actually okay. It doesn't matter. So you try to add T and T. If it's not doing, you throw an exception, and you throw the exception 42. Otherwise, I will just run the sum and return it, which returns T and added in two numbers. Another thing that I could see here is that void T is actually somewhere else. It's not part of my library. This is so general that it can be put inside some other namespace, like utility, or like in the standard library. The standard library will have this utility somewhere. You can use it. It's not part of your code. You just use it, and you use it here, the void T, and you just go to, and in your detailed namespaces, detailed namespace hide all these details from the user. Okay, they're not really hidden because the user can still go and look at your code, but is not supposed to look at it. And now this is the user code, right? This is the user side. This should be in another file, okay? The user include that library file and use it. And this code is exactly the code as we had before, only that is using my library namespace to find the functionality. Alternatively, you can do using namespace my library, and then everything will be fine. But this is the idea. So when you define a library that does something, you just encapsulate it into a namespace, you encapsulate into another namespace inside your library, something that the user should not be concerned of. And that's the only API you want to expose. And if we run this, did I compile this or not? Probably not. Okay, and there you have the exception, which prints an operator found. The program goes on and do the other operations. Now, this is not like something you really have to do like this, right? The error handling is up to you. So this is done with exceptions. Exceptions shouldn't be really used for error handling like this. It should be really for exceptional cases, like there's not enough memory or but this depends on the philosophy, really, that you want to adopt. But the idea is to isolate things and create abstraction layers. Now, all these template tricks that we've seen, and the namespaces and the inlining allows you to say that this code is as efficient as it can get. Everything will be inlined, everything will be smooth and clean. Now, the de-exception throwing might be a little bit of a problem, but apparently is not that big of a deal for performance reasons. But yeah. Questions? Okay, we're 5 minutes early, and it's time to go. Thank you.